Welcome to the 13th lecture of distillation, which is module 5. Before we go to the discussion on lecture 13, we just have a recap of our previous lecture. In our previous lecture, we considered the design method of distillation using Ponchon-Savarit method. Ponchon-Savarit method, and we discussed with an example how to calculate the number of plates required for a particular separation or specific separation. And secondly, we have discussed the distillation using packed column. Today, we will discuss on multi-component distillation. This is basically a preliminary introductions to multi-component system. So, we will discuss multi-component distillation. For multi-component distillation, if 3 component systems, then the graphical treatment can be possible if we use the triangular diagram. So, using triangular diagram, we can do the graphical treatment, but more than 3 component systems, the graphical methods becomes very complicated. So, graphical treatment method not desirable. In most of the practical applications, we assume liquid phase is ideal, where the Raoult's law can be applicable and equilibrium data can be obtained from the pure component data. This is in case of most practical applications we do that, but it is unsafe to predict detailed behavior from the pure component alone or from the binary systems. In this case, for rigorous calculations, digital computers are helpful for data analysis to predict the detailed behavior. The general approach to solve multi-component systems is similar to the binary systems what we adopted over there, that is one mass balance for each component and enthalpy balance are similar to those for binary systems. Equilibrium relations in this case is little bit complicated. Equilibrium data are used to calculate multi-component bubble and dew points, and the 2 limiting cases as we observed in case of the binary systems, that is the total reflux and minimum reflux. Similar to the binary system, it also applies in these cases. Rigorous methods which are available for multi-component distillations, that is using computers, but there are some approximates or shortcut methods which are more common for preliminary design. Today, we will discuss some of the shortcut method, how to calculate the number of plates required to get a desired separation. In this case, we will consider how many towers for multi-component systems are required. As we have seen, for binary system, one tower is used to separate 2 components into relatively pure components. But for multi-component systems, n minus 1 fractionators required for the separation of n components. That means, if we have a 3 component system, then n would be 3, n minus 1 is equal to 2. So, 2 towers are required for the given separations. So, this is the number of distillation towers required for a given separation. Now, design calculation method, feed conditions, temperature, pressure, composition, flow rate, these are either known or specified. Then there are two general methods. One is method 1, where desired separation or split between the two components, between two of the components are specified. Now, number of theoretical stages, this can be calculated from a selected reflux ratio. Number of theoretical stages which we require, this can be calculated from a selected reflux ratio. More than two components in the feed, complete compositions of the distillate and bottoms are not known. In this case, since the complete compositions of the distillate and the bottoms are not known for multi-component systems, so trial and error procedures must be used to obtain the compositions. How to do that? We will discuss that in next few slides. So, design method 2, where what are the things specified? The number of stages in rectifying section, number of stages in stripping section and the reflux ratio. These are specified and assumed is liquid flow rate, vapor flow rate and temperature for first trial. These are the assumed, and then this method often preferred for computer calculations. Now, Thiele and Geddes method, a reliable trial and error procedure to calculate resulting distillate and bottom compositions together with the tray temperatures and compositions. Thiele and Geddes methods are very reliable to do the trial and error procedure. Now, in multi-component systems, how to obtain the equilibrium data? So, equilibrium in multi-component systems. Experimental VLE data, vapor liquid equilibrium data, which are not known in most multi-component systems. Generally, these are computed from available equations or correlations. So, it is not known and generally it is computed. Ideal behavior may be assumed, so that Raoult's law is applicable. And as we know, for hydrocarbons of a homologous series form nearly ideal solutions. Now, for jth component, in an ideal solutions, we can write y j star p t is equal to p j star is equal to x j p j v, where x j is the mole fractions in the liquid phase, p j v is the vapor pressure of component j at a given temperature, and p t is the total pressure. So, then p t for n component, number of component if n, it will be summation over I is equal to 1 to n p I star. So, that is the total pressure. The vapor pressure of the components in the mixture are known at a given temperature. Therefore, for a particular liquid composition, say x 1 to x n, the vapor compositions can be calculated. From these equations, y j star is equal to p j star by p t is equal to x j p j v divided by summation over I is equal to 1 to n p I star. We know that relative volatility between the component I and j is alpha I j, which is equal to p I v divided by p j v. And if we substitute these relations in these equations, we can obtain y j star is equal to x j divided by 1 by capital P j v summation over I is equal to 1 to n x I p I v, which is equal to x j divided by 1 by p j v summation over I is equal to 1 to n alpha I j x I. We can also write x j alpha j I divided by 1 by p j v summation over I is equal to 1 to n alpha k I x k. So, once the equilibrium vapor mole fractions are known, the partial pressure and the total pressure can be calculated from these relations. For multi-component systems, generally the equilibrium data is defined in terms of the distribution coefficients. For component J, Mj is the distribution coefficient which is equal to Yj star divided by Xj, and this Mj also depends on temperature, pressure and compositions of the mixture. And the relative volatility we can write alpha ij would be equal to xj star by xi divided by yj star by xj, which would be equal to mi by mj. For ideal solutions at moderate pressure, m is independent of compositions and only depend upon the temperature and the total pressure. So, mj is equal to pjv by pt, and then alpha ij would be equal to piv by pjv. Now, we will look how to do the bubble point and dew point calculations. For bubble point calculations, if it is bubble point vapor, summation over yi star would be equal to 1.0. So, we can write ma xa plus mb xb plus mc xc and so on would be 1.0. Now, if we consider J as the reference component, we can write ma xa divided by mj plus mb xb divided by mj plus mc xc divided by mj and so on would be equal to 1 by mj, or we can write alpha aj xa plus alpha bj xb plus alpha cj xc and so on would be equal to summation over alpha ij xi would be equal to 1 by mj. Bubble point vapor composition which can be calculated yi would be equal to alpha ij xi divided by summation over alpha I j xi. If the liquid composition and total pressure is fixed, the calculation of temperature can be made by trial and error satisfying these equations, and its convergence is very rapid since change of alpha with temperature is very slow. We will discuss this with an example. The dew point calculations, which is similar to the bubble point calculations. For dew point, summation over xi would be equal to 1.0. So, we can write ya by ma plus yb by mb plus yc by mc and so on would be equal to 1.0. Now, if we consider j as reference component, so mj ya by ma plus mj yb by mb plus mj yc by mc and so on would be equal to 1. So, we can write alpha aj xa plus alpha bj xb plus alpha cj xc and so on would be mj, and the equilibrium dew point liquid compositions can be written as xi is equal to yi divided by alpha ij divided by summation over yi by alpha ij. Let us take a very simple example, a solution of hydrocarbons at a total pressure of 350 kilonewton per meter square, which contains 5 mole percent N propane, normal propane, 30 mole percent butane, normal butane, 40 mole percent normal pentane and 25 mole percent normal hexane. Compute the bubble point and dew point. For bubble point calculations, the following steps can be followed. First, we have to estimate the bubble point, and to estimate that we have considered 60 degree centigrade is chosen. At 60 degree centigrade and 350 kilonewton pressure, we have to get the corresponding distribution coefficient m, which is given in column 3 for different components. So, distribution coefficient is given. Reference component is chosen to be pentane in this case. Pentane is the reference component, whose relative volatility we can see alpha I is 1, which is given in column 4. Column 4 lists the relative volatility here. So, we can see alpha C3 C5, the relative volatility between these two is 4.70 divided by 0.62, which is around 7.53 and so on. Between this, if we know the distribution coefficient and we know the relations between the distribution coefficients and alpha, and we can obtain the relative volatility for each components. And then we can add up the sum of alpha I C phi x I, which is given in column 5. If we take the sum of all these, which is around 1.702, and then with corresponding to that 1 by 1 point this is the 0.588, which is reported in column 6. Mi values is very close to the temperature which can be obtained from the monograph is around 56.8 degrees centigrade. Calculations are repeated for this temperature in column 6 to column 8. If we see column 6 to column 8, so these calculations are repeated and we can see MC5 is 1 by 1.707 is equal to 0.586, corresponding to 56.7 degree centigrade, which is nearly equal to 56.8, which is the assumed. And then this temperature is matching the assumed temperature, then this temperature is known as the bubble point temperature, and corresponding vapor compositions is given in column number 9. So, the last column which corresponds to the vapor composition. Similarly, for dew point calculations, similar steps as we did for the bubble point calculations are followed, and in this case assume the temperature say 80 degree centigrade, and when summation over y I by alpha I C5 would be equal to 1.081, which is MC5, and then we can get the corresponding temperature T is equal to 83.7 degree centigrade, and then we can repeat the calculations which will give around MC5, which is around 1.103, which correspond to the temperature of 84 degree centigrade, and which is nearly to the assumed temperature 83.7 degree centigrade, and hence the dew point is 84 degree centigrade. Now, we will discuss about the multi-component flash distillation. This is a typical flash distillation column we have discussed before. We have a heater and then the feed is heated and flashed inside a distillation column, and then we have a distilled vapor and the bottom liquid. If we define the fraction which is vaporized is F, F is V by F, then the fraction of the feed which is remaining as liquid is 1 minus F, which is L by F, and if we do the component balance, Y I would be equal to F minus 1 by F x I plus x I F divided by F. If we combine equilibrium and operating equations for multi-component systems, as we have seen, Y I would be equal to K I, x I would be equal to K C, alpha I x I, when alpha I is K I by K C. So, component balance equations in this case, if we apply this, this will become Y I would be equal to K C alpha I x I would be equal to F minus 1 by F x I plus x I F by F. And if we solve for x I and sum for all components, the summation over x I would be equal to x I f divided by summation over f k c x I minus 1 plus 1 would be equal to 1. This is solved by trial and error by first assuming a temperature if the fraction of vaporized is set for a particular value. The iteration procedure is similar to the bubble point and dew point calculations. What to do? Assume a plus temperature, determine k values at the temperature and then compute the summation. If the summation is not equal to 1, adjust the temperature and repeat. By trial and error method, we could obtain the flash temperature. The final values of T and K's are used to determine the product composition. Now, in multi-component distillation, another important parameter is the key component. Generally, two key component is selected. One is known as the heavy component H and another component is the light component which is designated as L. Key components must be present in both the overhead and the bottoms. Light components, the more volatile component with respect to the light key components are called the light components and that will be present in bottoms in small amount. And heavy component which is less volatile compared to the heavy key components and that will be present in distillate in very small amount. The two key components as we have selected heavy key or light key, they are present in significant amounts in both the distillate and bottoms. Now, non-key components, everything but the keys, they may be distributed if they occur in both products or non-distributed if they appear in only one product. Remember, keys must be distributed, but non-keys may be distributed when they have volatilities very close to keys or between the keys or when the desired separation is very sloppy. So, two key components are very important to select for getting a particular distillation calculations for multi-component systems. Now, for multi-component systems, how to obtain the minimum number of stages? As in binary distillation, the Fensky equations can be used for multi-component systems to determine the minimum number of stages for a given separation at a total reflux. Equations can be written for any two components. In general, apply the equations to the key component and solve for the number of stages. If we apply for the key components, n mean would be equal to log of x L d into d divided by h x d into d multiplied by x h w into w divided by x L w by w whole divided by log of alpha L average. Now, x L d is the mole fractions of the light key component in the distillate, x L w is the mole fractions of the light key in the bottoms, x h d is the mole fractions of the heavy key in the distillate and x h w is the mole fractions of the heavy key in the bottoms. Now, H alpha L average is the mean relative volatility. This is used when alpha is not constant. Normally, a geometric mean is the best. So, for geometric mean alpha L average, you can write between the heavy key and the light key, it is root over alpha L d into alpha L w. Once the minimum n mean has been established, same equations can be rearranged to determine the splits of the other component in the mixture as given below. So, x I d into d divided by x I w into w is equal to alpha L average to the power n mean into x h d into d divided by x h w into w. By this way, we can determine the split of the other components as soon as the n mean is obtained. Now, minimum reflux. The minimum reflux calculations are based on invariant zones around feet where composition stops changing. These are similar to pinch point idea used for binary columns. One way to determine the minimum reflux ratio for binary system is to assume a pseudo binary system. This is done by creating a hypothetical feet made up of key components. First, we have to assume pseudo binary system, and then we can use the McCabe-Thiele method. To determine the pinch point and minimum reflux. We know that at minimum reflux R minimum, the number of stages required is infinite. Number of stages required infinite for a given separation of key components. But in this case, for binary systems, we know that there is only one pinch point for binary. But in this case, there will be two pinch points, one is above the feed plate, one above feed plate and another one below feed plate. The rigorous procedure can be applied to calculate RM by trial and error calculations, but that is very tedious for hand calculations. Often the minimum reflux or mean can be determined by under-root shortcut method. This method also assumes equimolar overflow and it defines the relative volatilities of each component relative to some reference components, and they are usually the heavy components. Using the average alpha values and assuming constant molal overflow, these are the following equations: 1 minus q is equal to summation over alpha I x I f divided by alpha I minus theta, and then R m plus 1 would be equal to summation over alpha I x I d divided by alpha I minus theta. So, these two equations should be simultaneously solved to obtain the minimum reflux ratio R m. So, x I d are supposed to be the values at the minimum reflux. Alpha I may vary, which can be assumed, or the average values can be taken, which you have discussed before, and alpha values for heavy key, which is considered as 1. So, from this we can calculate R m by trial and error method. Now, how to obtain number of stages for a given separation? The shortcut method requires an optimum R reflux ratio, which can be obtained from the empirical correlations. Then we can use the Gilliland plots, to find the actual stages required for a given rate. For a given reflux rate. The plots relate two variables, one is x, which is equal to R minus R mean divided by R plus 1. This x ranges from 0, x is equal to 0 at R is equal to R mean, and x is equal to infinity at n is equal to n mean. So, y is equal to n minus n mean divided by n plus 1. This is ranges y is equal to 1 at R is equal to R mean, and this equal to 0 at n is equal to n mean. This way we can obtain the number of stages required for a given separations. Now, how to locate the fit rate? Kirkbride derived an approximate method to calculate the number of theoretical trays above or below the fit, which can be used to determine the fit tray locations. This is an empirical relation, which is log of n r by n s would be equal to 0.206 log x h f by x l f into w by d into x l w by x h d, this is square. So, the x h f, x l f, w d, x l w and x h d, which are defined before, it has similar significance. N r is the number of theoretical trays in the rectifying section, and N s is the number of theoretical plates in the stripping section. Then from this we can obtain the location of the feed tray. Thank you.